In chemistry, depending on the course, you might find reactions classified in one format, whereas in another course you might find them in a different format. In survey courses like this, typically the organization of and classification of reactions is in the following list, okay? You'll find composition reactions, decomposition reactions, single replacement, and double replacement or metathesis reactions. Now this leads to two very broad categories in each one of these. The first three are oxidation reduction reactions. However, this last class of reaction, double replacement, is also a metathesis reaction. Is just that, a metathesis process. In other words, no changes in oxidation states occur as you go through. Now, if you go into another course, and this is always a little short thing that I give, organic chemistry, for example. The reactions in organic chemistry are typically classified by what they call reaction mechanisms. Okay, there's a simple acronym that I tell everybody, and I don't go any further than this on this. SEAR, like Sears and Roebuck. Okay, SEAR. S stands for substitution, elimination, addition, and rearrangement. Now that's as far as I'm going to go with it. I'm not going to go into all the mechanisms and stuff of this thing, but if you do go on to organic chemistry, you might remember that. Oh, I remember that little acronym he gave me. It classifies the reactions, and then of course you stuff all the details in. Well, our efforts will be localized in this classification, and I'm going to go through each one and we'll develop your skills in that. And it's very important because all of these classifications start bringing together everything we've talked about, from atoms, elements, compounds, molecules, writing formulas and balancing equations, and on and on and on. And that, of course, as you know, will be used through the entire course, Chem 1 and Chem 2. For decomposition reactions, a composition reaction is just a reverse of a decomposition reaction. So we're really talking about two types. If you turn a composition reaction around, is simply a decomposition reaction. Well, here's a little simple acronym that I recommend students, and you spend a few minutes with this against the type. You'll remember, hopefully, the types and what they will ultimately generate. COACHE, Coach E. Okay, so this is decomposition reactions. And COACH And I skipped the E because it's called electrolysis, actually. And so this is about carbonate decompositions. This O refers to oxides of metals. Acids, these are weak and strong acids or molecular acids. Now this is one of those analogous series terms, chlorates, bromates, and iodates. Hydroxides, and finally electrolysis. And so what you have to do is learn this list as well, what does a carbonate decompose into? Or what does an oxide of a metal decompose into, or molecular acids, on and on like that. Well, if you look at the formula of the compound, it will tell you what it will break down into. Conservation of matter. Carbonate is a CO3 polyion, as you know hopefully by now, and you hook that up with one of the metals out of the periodic table, something on the left of the chart, and you can pick any one of them. We'll take sodium carbonate, for example. Okay, so there's, and I could pick chrome carbonate or nickel carbonate or any metal out of the transitions, or group 1, group 2, or even group 3, aluminum carbonate. So they exist. And so the learning just how this functions for one should apply to all of those as far as predicting the outcome of that decomposition. Well, what is this composed of? It's composed of a metal, a non-metal, and an oxygen. And typically these will break down into a metal oxide and a non-metallic oxide. Carbonates are notorious for generating CO2. So this would break down into a metallic oxide, NaO plus CO2. Now you have to have the subscript because that's a +1 and oxygen is -2, so you had to have two of those just to remind you that the principles of sum of charges equals 0 still apply as we go through these concepts. So in a general way, you can look in your notes, carbonates hooked up with metal always give you a metal oxide and CO2. Oxides of metals refers to any metal up on the periodic chart connected to oxygen. Okay, so if you're talking about iron 2 oxide, that'll be a 1-to-1 reaction rate. Iron 3 oxide, good old down home rust, iron Fe2O3. So it doesn't matter. It's a metallic oxide. Now, the issue with metallic oxides, I'll bring those down here and we'll list them. And we'll start with the iron oxide, and then we'll follow with the iron 3 oxide. What do they break down into? Well, looking at it, there's only oxygen and iron, and so you're not going to stay in the oxide form, so it's going to split. If it's a decomposition, it's breaking down, right? So you have iron and oxygen. So in the same way here, you'll have iron and oxygen. Now, is that the proper form? Well, you get the textbook, and you look back in the thermodynamic properties. Now, what's the standard state of iron? Well, it turns out to be this in both cases. So we've got to use that. That's what I told you in the last lecture. when you write a molecular formula of some kind of reaction, the substances that you use in these formulas must be in standard state. Well, what's the standard state of oxygen? O2. O2, because you've learned about the 7 diatomics, so we know now you can just automatically hang that diatomic on there real quickly. Then you balance it by inspection. Well, I've got an FeO going to Fe plus O2. Well, I got to have 2 over here, and I can put a 2 here. That should have been a 3, sorry. 3 right there. So I need 2 iron. Well, I actually got 3 oxygen. So what I'm going to do is bring 3 and 2 right here and put a 4 right there. So, you know, once you get the yield of the substance, then you can pretty well predict what the balance is in standard states. Acids, molecular acids. We'll come down here, do this one. Now, what I'm about to tell you is for molecular acids. Molecular acids are common acids that are based on what we call the Arrhenius theory or Bronsted-Lowry theory of acids and bases. We'll get to that later today if we have time. In that, all of these deliver hydronium ions into aqueous solution, hydrogen. So for a molecular acid, these function to deliver increasing H plus ions. That's the character of it. Acid is an acid for 2 reasons. It ionizes and it must be in water. Those are the 2 reasons. If it's not in water, it's not an acid. So because there's no ionization. There are side products that generate HCl's and stuff, but they're gas phase out of a reaction, and they're scrubbed into a water environment like that. Anyway, molecular acids are divided into what we call electrolytes. There's strong electrolytes and weak electrolytes. Strong electrolytes are characterized by 100% ionization. You will find no molecular forms of that substance in the solution. HCl will break up 100%, and you will not find any HCl molecules floating around. And there's also weak electrolytes. Electrolytes comes from the process of conducting electricity. In other words, these compounds ionize and function to conduct electric charge if a charge is put across the solution, a potential difference. These are ionized less than 100% ionization. Most of the weak electrolytes are usually less than 1.5%, 2%. So there's a big differential in here. Now, what I'm about to give you is something you've got to memorize. Like it or not, it will depend. It will govern whether or not you can handle certain questions on the test. The strong mineral acids. Now, there are other acids in the universe that are stronger than what I'm about to give you. Antimonic acid, for example. I mean, you can't find anything to put it in. It's so strong. But these acids are the most common that we're using in this course. Okay, and there are 6 of them. I call them the big 6 or the 6 strong or the strong 6. That's HCl, HBr, the halogen acids, and HI. So that's easy to remember. But then you have to remember NO3 from the nitrogens, nitric acid, hypochlorous acid, no, not perchloric acid, sorry, HClO4, and H2SO4, first ionization step. So the fact that molecular acids in some cases are diprotic. These are monoprotic acids. They only deliver 1 hydrogen off of the molecule. but the H2SO4, H2SO3s, the sulfurous acid, and those will deliver more than one hydrogen. When they do deliver more than one hydrogen, they deliver them in what we call steps, ionization steps. And it's called a first ionization step, and then the second ionization step. So it would be like this, H2SO4, and one of the hydrogens comes off and generates H plus HSO4 as a product. And then HSO4 minus will go to have another, it would be acidic in its nature, and deliver a hydronium ion, and you would have an SO4 2 minus left out there. Now, the first one, notice I just put one arrow. Second one, I put two arrows. The first one with one arrow means that's the 100% ionized form. It is the strong acid. That's why I wrote down here first ionization steps, 6 strong acids, HCl, HBr, HI, HNO3, HClO4, H2SO4 to the first ionization step. But that second ionization step does not ionize 100%. You will find in solution the bisulfate ions floating around in there. Okay, if that's the project you're working on, along with quantity of hydronium ions and sulfate ions. So all three would exist in that second case. Now, so we have the 6 strong acids. Well, how do you identify weak acids? Acids, it's real simple. Acids not members of the strong 6. End of it. Doesn't matter whether you know what it is or not. For example, if I gave you HC2H3O2, when you look at this, this is your ionic hydrogen. Okay, so it's like an acid. But is it a strong acid or is it a weak acid? It doesn't matter whether you know what it is or not. It's not a member of this collection up here. And so, yeah, this is a ionizable. That's the way these are typically written, which says this is an acid, but it is a weak acid because it's not a member of the strong 6. In this textbook and many textbooks, they write acids in various forms, but you'll see for the most part acids written with that ionizable hydrogen and in the front of the formula. So if you look at all of these, you see every one of them have a hydrogen out in front of the formulas like that. That's the one that breaks away. Now you have some that have hydrogens buried more back into the formula. I can't even see over there. Yeah, here, right here, or up here, and here. Those are non-acidic. And there are parts of the anion that comes off, because if you were to ionize it, you'd break off the hydrogen, and then everything else would be the polyion that's left over. Now, if it has a second ionizable hydrogen, it will show it in the front end. Here's a 3 triprotic. So it has 3 ionization steps. So you take each one separately. So I'm just showing you what the nature of this is, and we'll cover this again shortly. What do they break down? So if you're given something like H2SO3, is that a strong acid or, sorry, thank you. Okay, is that a strong acid or weak acid? It's a weak acid. H2SO4 is a strong acid. So, hint, quiz day. Okay, what is this made of? Hydrogen, oxygen, and a sulfur. Well, it's going to come all to pieces into, well, you don't have hydrogens jumping out of there in gas form if it decomposes. You don't have sulfurs jumping out by themselves, and you might think you've got oxygens, but it's all in water. It has to be in water, otherwise it would not be an acid. So in water, these are not going to break down into hydrogen in basic standard state, sulfur in standard state, and oxygen standard state. It's just not going to happen. There are other reasons, but that's good enough for right now. So what does it break down into? It breaks down into a non-metallic oxide and water. Every time. Every acid will go to a non-metal oxide and water. Non-metal oxide and water. Well, the only other one is the non-metal in here, the sulfur. So this would have to go to SO2, and it will be a gas, and it'll come out as a gas, and then it will make some water, H2O, liquid. So when you look at the acids, C2H3O2, okay? What is that going to make? Well, it's going to make CO2 and water, whatever the balance is. In an aqueous solution, if you heat it up and break it down, it'll go to CO2 gas, a nonmetallic oxide, and water. So just look at what it is. In water, it's not going to break down into basic standard state like this. So to try to give you a little heads up on how these acids function, we'll be using this many times through the course. Hopefully that makes sense. And please spend some time kind of understanding those. Okay. The next class is the analogous series. Of compounds. And that, of course, is your chlorates. That's your ClO3 minus set. And bromates. All I'm doing is substituting the halogens. Like that. Well, the overall charge is a -1. Now, what kind of compounds would this make? Okay. If it makes an acid, it'd be HClO3, HBrO3, and HiO3. Now, if it's a salt, which is a metal, non-metal, non-metal being the polyion or ionic compound, then you could say sodium chlorate and sodium bromate and sodium iodate, like that. So then you look at, well, what will they break down to? Well, if it's an acid, that is HClO3, like that, it does the same thing as I just told you. Non-metallic oxide and water. So that would have to go to a ClO minus plus H2O. It's going to a non-metallic oxide. And then the salts, if it's a metallic salt, let's just not put it in water this time. I'm thinking this might be, no, this is not in water, it's solid form. That's not in water. That would go to an HCl gas, like that. So it would be a hydrogen, whatever it's hooked to, and then the water. Sorry. The salts are something like potassium chlorate, and this type of compound. And it's a solid. And if you heat it, this little delta sign above the arrow means heating strongly. Take a Bunsen burner and nuke it in a test tube. It's going to break down into a salt and O2 gas. Well, the only salt in here would be your KCl. So this would go KClO3 as a solid would go to KCl solid plus the O2 gas. Well, you got to work on these, see how they work. But you can look at the compound for the most part and say, okay, what do I have? I got a salt, a potassium chloride, and oxygen. Well, this typically breaks off the oxygen and leaves the salt right here. We need a 3 here and a 2 there and a 2 there. Okay. So the main thing is salt and O2. Now you probably won't see this. This is a rarity. Okay. So now what you should do is translate these into the bromates and iodates. This would be KBr, Ki, and then the oxygen. It's the same idea. As I've gone through these, I've asked you to look at the compound and try to get an idea of what it goes to. And when you have a hydroxide like this, it's a metal plus the polyion. So any metal connected to the hydroxide ion is the hydroxide, metallic hydroxide. You can have sodium hydroxide, calcium hydroxide, but that'll have to have a subscript of 2. Magnesium is quite frequently used in these. Now, when these are heated as from solid form, what do they go to? Well, all of them are bases. This hydroxide indicates a base. Many of you know that. Something that has an OH group in it. In this context, hooked to a metal, it will be a base, an alkaline system. If that OH is hooked to a non-metallic, it's called an alcohol, like methanol, ethanol, whatever. But if this is hooked to a metal, then it's a base or an alkaline compound. When they break down, they all generate water. Well, the only thing left is the metal. But in context, these will go to a metal oxide and then also water. So this would go Na2O, this is CaO, calcium oxide, magnesium oxide. You can balance it. So it's a matter of kind of just looking at what you have and studying it enough that you can predict the outcome of what these decompositions will be. One that's very important is the decomposition of what we call a weak base. Excuse me. Decomposition of a weak base. Well, this is the only non-metallic cation that you'll see for right now. There are other cations of a nitrogen derivative, but it will come off as ammonia gas and water, but it's still, all of them produce that water molecule as it comes off in the decomposition. We'll see that again in a few minutes under gas decoms. The last one in this collection are electrolysis. Electrolysis of salts. When I say salt, I'm saying also ionic compound. And an ionic compound, as you remember from the nomenclature flow sheet, is a metal plus a non-metal component, and that includes the polyions that are anions. When a salt goes into water, it undergoes ionization. That's why it's called an ionic compound. neutralize, and this gives you cations plus anions. Cations are the only one that have a plus in the term. Anions don't, but they are the opposite charge. When these are in aqueous solution and electrodes are inserted into the solution and connected to a transformer or a battery, charge will move by oxidation reduction process, which you'll learn in Chem 2. But the nature of this, when that process takes place, oxidation reduction, it converts the ions into basic standard states if they are substances like sodium and chloride. Sodium chloride in the melt, call it liquid, salt melts, that's table salt. When it melts, will undergo a breakdown into cations and anions, like that. Now, one of them will have to, all of them are converted to basic standard states. So when the electrolysis converts ions, I should say element ions, into basic standard state forms. Might use this as an example here. And we'll draw an electrode like this, and we'll hook. Okay, there's your electrolytic cell. Right there. Now what you have in here is a bunch of cations and anions floating around in there in the melt form. So in this melt form, when you connect it to a battery, the negative pole makes this electrode, whatever it is, it's usually graphite electrode, it'll make that electrode negative, give it a negative electrostatic charge. And then the positive side will be positive. So opposites attract, as you well know. Negatives are attracted to positives, and positives are attracted to the negative. So this sodium will come over here and this chloride will go over there. Well, the sodium is deficient in electrons because of the positive charge. And so it will gain an electron and go to basic standard state, like that, as a solid. And the chloride right here has a surplus of electrons because it has a negative charge. That's what the positive and negatives do. You have a positive that's deficient in electrons, it wants to gain electrons. And those which are negative charged, they want to deliver their electrons. And so the chloride wants to go to its basic standard state, but that's Cl2, and so you have this reaction for that one, and you have to have two of those. Now, when you add this together, you have to add it so that, as I shown you earlier, add it so that the charge is balanced. So I need to multiply through this equation by 2. So that will allow me to cancel the electrons out, and so I have 2 sodiums plus 2 chlorides going to Cl2, actually gas comes out, and 2 moles of sodium solid. And so on this electrode right here, you would see gases, bubbles coming off of chlorine gas. And over here you would see a coating of sodium metal. Now that's the simplest form of electrolysis. But what to remember is electrolysis gives basic standard state of elements. And where do you find those forms? They're like in the back of the book. I'll have them at the bottom of the questions, and you won't have to have the text. So you just look at the, well, what ions do I have? Well, that's going to sodium, and what's that one going to? Well, that's got to go to chlorine. That's what the basic standard state is. And that's true for all the halogens, and if you electrolyze something with nitrogen, it'd have to go to N2. So electrolysis is the taking, say, sodium chloride, ionizing it into its ions, and then running a current through it and making the basic standard state form. That's a decomposition. You might write it NaCl aqueous goes to Na solid plus Cl2 gas, and you balance it in like that if you want to. But it is the process of decomposition. And if you turn these around, of course, that would be a composition. You can have a reverse reaction, which will force these into ionic